Alright, so in this tutorial I'm going to show you how to use Gauss law. So we are going to consider three situations: a very infinite line, and then infinite surface, cylindrical surface, and infinite volume, surface volume. It's a cable, for example. So Gauss law suggests the flux, electric flux, throughout a surface, a closed surface, this one. So the surface, as we said in lecture, for reason of symmetry, could be a sphere for point symmetry, or axial symmetry for a wire. That's our case. So that flux can be evaluated in two ways: either the field dot dA, or the sum of all enclosed charge inside that Gaussian surface, epsilon 0. This S here is the Gauss surface, and this is what I want to understand. We are talking about two kinds of surface here. For example, if I consider second example, this one, we have the surface of the object, which is the cable, for example. It has surface and the Gaussian surface. The flux under consideration is the flux through these walls of Gaussian surface, not this one. Alright, although we may discuss whether the same or not, but this is the thing. So we have to answer. Now you are going to see why is it important. So first, let's evaluate the field here at distance rg from an infinite charged line. So notice here, the field will always be normal to the structure, so I expect the field outward because the charge is negative, positive. Here the two bases, the A is outward and E is perpendicular, so the dot product is 0 here. So the flux contribution of the base is 0 on both sides, equals 0 here, and also the flux through this base is 0. There is no contribution. Now, if I want to apply here, by the way, this is also A, which is parallel to E, so the cosine 0 is 1. The flux is maximum on lateral surface. So, what I wanted to understand is that here, the E dA cosine 0, just E dA, and the integral of the A, just A. So I'm going to write E A equals the charge on the line, which is Q over epsilon 0. Now, this is easy. Now, what I want to understand this point is very important. To understand this A is Gauss. So what does this mean? I'm talking about this one here. That's the surface A. And explicitly, since this is a line, this is actually lambda L over epsilon 0. This is the linear density. Now, what is A? A is the lateral surface of this infinite cylinder, which is Gaussian surface. If you open this green cylinder, you end up with something like this, a rectangle. This is, so this is Rg. So the circumference is 2 pi Rg, that's circumference, and this is L, and the area is just pi. So I will have A times 2 pi I Rg. That means the radius of Gauss surface, which is the distance we are looking for, the field, times L, that's the area, and then equals to lambda L over epsilon 0. Now I can reduce at this point, so I lose L and L, and that's it. So I can write now E, probably have to write with red, much better. So E is just lambda over 2 pi epsilon 0, and then I have Rg. And so this is the field, electric field at distance rg, I can call it y, a, or anything, from the infinite charged line using Gauss law. I hope this would convince you how to use Gauss law, what is the surface of Gauss versus the surface of the object. In this case, we don't have surface, linear charge. Now, let's apply this reasoning now to the second object, which is also cylinder. Imagine a cable, but they have surface density eta. Now, in this case, we are going to do the same thing. The area of Gauss, still the lateral surface of the cylinder, which is 2 pi RGL. L is the length of the cylinder, both Gaussian surface and the cable inside. But the surface will be different. Q is eta A prime. What is A prime? In this cylinder, the radius is A from here to here. And so the area would be eta times what is the area? So it's just pi a squared. No, 2 pi a. This is a mistake. It's not a squared. So 2 pi a. That means the circumference here, this circumference, times L. That's the L lateral area. This area here, this area I prime is this one. Okay? Because the charge is here. There is no charge on the Gaussian surface. The Gaussian surface will have the same quantity, 2 pi RGL. So now all we have to do is plug this one in the equation somewhere here. So let's use the... Alright, so let's use this one. So E, the area will not change, the Gauss area, 2 pi Rg, that's the circumference, times L, that's the area, equals, so now we have eta, 2 pi, then A, the radius of the cylinder, and then L, all this divided by epsilon 0. Now from here you can make simplification, evaluate what is E. I'm not going to do it, it's very simple. You lose 2 pi here. Okay, let's do it very quickly. So you lose 2 pi, you lose 2 pi, and then you lose L, and you lose L. So basically E, the electric field at distance, is just eta times A, the radius of the cylinder, of the charge, divided by Rg, and epsilon 0. Alright. Right. I think so you did the same thing for the remaining. So on the second part, so this is the field now. Obviously this is the field due to a surface density here. Now I can do the same thing for the volume. Imagine this is a non-conductor material, it's completely charged. You can expect the charge inside. The only difference is that here rho v prime, and prime is the volume of this cable. Now what is the volume? Obviously the volume will be, so rho times pi a squared, that's the area of the base, times L, that's the volume of this cylinder that we are going to plug for the electric field here. So E, the area will not change, the area of surface of Gauss, that is 2 pi rg. G stands for Gauss, that means this distance here from the center of the cable to the point of interest, times L equals, now the charge is Q over epsilon 0 and the charge is rho, so this is rho, and then pi a squared times L, all divided by epsilon 0. And at this point we can now probably go ahead and simplify. So probably we are going to lose L, of course. We are going to lose L and L. We'll have with pi and pi. So the E, I'm running out of space here, so it's just rho a squared, that's it, divided by, so 2 rg epsilon 0. So this is the field due to a volume surface density of the cable. So this is, I hope this will clarify a little bit. It's cumbersome, but you can understand Gauss law applied to almost the same symmetry, a cylinder, actual symmetry, but here we have infinite charge line. Here is a surface, imagine a cylinder, hollow cylinder, which has a charge on the surface, therefore the charge is eta n I prime, and area of the object, not the surface of Gauss. Now if you have volume density, then you consider rho v prime, or the volume of this object. Notice the structure of the field will be different in each case, but understand the Gauss law involves the surface of Gauss and the surface of the material, different things. I hope this will help.